Well, what is a TGA? Some people got mistaken. A TGA is something that it's a weighting scale inside of an oven. And in the oven, we can also control the temperature. So we have an oven that heats in a constant rate over time, and you measure the mass over time. At the same time, you can control the environment inside of the oven. And that's very important, as we are going to see. This is a TGA from Mettler Toledo. I'm not really familiar with Mettler Toledo, so we use Netch. So we have a Netch in the lab. Yeah, actually, we have two. So we have the weighting scales are down here. They measure milligrams. And over here, we have the oven. And it's controlled by the computer. So you set up, saying, OK, 10 degrees per minute of heating rate, and it's going to do 10 degrees minutes per minute for heating rate. And at the same time, it records the weight. You have, in this case, you have the possibility of flow with 3 gases. So you can, normally we do in nitrogen, that is non-reactive atmosphere, but you can do in oxygen or CO2, depending on what you really want. So you control the atmosphere, you control the heating rate, and you record weight over time. This is one thing you record. You can record other things. So we have first decisions, sample holder. If you go to high temperature, you have to use platinum. It's costly, but it's quite effective. We use a lot of aluminum oxide that most of the TGs we have goes to 500 degrees centigrades. So this can go to 2000. So you don't really need platinum. And you can use aluminum for low temperature. We mostly use for gypsum. That is handy. We have some different crucibles for different sample size. The largest that I know is this one from Netch. They can put 1 gram of cement inside of it. But the most common in the market, perhaps, is the 70 microliters that you put 20 milligrams. There's a huge difference in terms of sign and the amount of, with the weight loss. Since the scale is the same, so you got more sensitivity in one than in the other, but it is going to influence the peaks, the temperature of the peaks, and of course, here you are much more sensitive to small amounts because you have more weight. But the peaks are much wider. You're going to see it. How does it work? Well, what we record is mass change, and mass change, it's water loss. So drying properly without destroying the sample is very, very important. You have to dry it, but you cannot dry it too much. You decompose ettringite, and there is a lot of water on ettringite. You lose a lot of water of calcium silicate hydrate because the water is not chemically bound, it's absorbed. So you have to be very careful on drying. Mass change due to chemical reaction. If you heat calcium hydroxide, portlandite, it's going to decompose around 550, depending on your TG. You decompose calcium carbonate, you decompose magnesium carbonate, and everyone at different temperatures. You can also have oxidation. If you have oxygen inside and you're dealing with slag, you can have oxidation of sulfur, and then you got weight gain in the system. It happens. So some machines allow you to make a vacuum before. You remove the environmental air and then you pump nitrogen. So you prevent this kind of oxidation problems. And if you have organics inside, and nowadays you always have some organics inside, like the superplasticizer, could be plastic fiber, or even carbon from fly ash. So you can have other things happening inside of the system. Or if you are in mortar, you can have a polymer, like 10% of polymer inside. And this polymer is going to decompose, release carbon, and it can even easily carbonate calcium hydroxide inside of your machine. So we also make, so you record weight over time. You can make the first derivative of the weight over time, and you got a DTG, and it's very handy. Some machines, they allow to record, make DTA, is a differential thermal analysis. I think 25 years ago, everything we got was DTA. It's a very simple machine. You have one inert sample and your sample, and you measure temperature inside of both samples. Inert sample will be aluminum oxide most of the time. So it's heating in the same oven, but because you are losing or gaining mass and you are exchanging weight with the environment, your sample temperature is going to be different. Every time you got, it's water is leaving the sample because the temperature is high. So your sample will be cooler than the other sample that is inert. So it's difference of temperature. If you go to old manuals or thermogravimetry or thermal analysis, is going to be most DTA. And nowadays, the new machines, it's a dynamic or differential scanning calorimetry. It doesn't measure temperature, it measures heat flows. So if your sample are releasing heat, meaning it's getting cooler than the other sample, that's the reference sample. So always comparing heat flow. Here you just see mass changes. Here you can see allotropic transformation from quartz to tridymite to cristobalite. You see it, no change of mass, but there's a reorganization, and you always got no heat flow or temperature difference, and this can record that. You can record glassy blast furnace slag becoming a crystalline material over time in the temperature, so you can understand what's going on. Okay, typical output, temperature. Sometimes they put time here, and then you have the heat rate. So it's much better to put temperature and weight. Weight, the normal way to present it is a percentage. 100% is your weight in the moment zero. Then you start heating stuff. This is quite dry. And temperature goes up, and then reach 400 degrees centigrade, start to decompose. Part of the material goes up, so you have less weight, less mass, and then it's almost stable. This is a portlandite decomposition. This is calcium hydroxide pure in TG, probably with nitrogen in the flow. The derivative of it, DTG, you can see where the peak arrives, it starts. It's clear. There's some weight loss here, but not much. Comes here to here. And then you can make a calculation of the weight difference and express with the equation. You can have DTA, differential thermal analysis, and DTG. This is temperature difference, and this is derivative of the weight. It's a completely different thing. In this case, it's almost the same, but it's not the same. And people use as the same, but it's not the same. You cannot do it. It's a different phenomenon, and this is just good to see how DTG is the rate of weight change, how fast the material is losing or gaining mass. And this is about heat loss. Heat is not weight, so it's completely different stuff. Nice things that we need to have, if you put in the vent of your TG a mass spectrometer, you can measure the chemical composition of the gas that is coming out from the system. Okay? And so they did this here. They started to heat the sample. In the beginning, 100 degrees, water, 0 CO2. Okay? Then peak of water, this is probably CSH and ytringite. Then it goes. Another peak of water, portlandite decomposing. Very sharp peak, very clear. And let's say 550, 600 degrees, CO2 starts to show. You see here at the same time you have a water flow and CO2. So that there is an overlap on it. There is an overlap on it. But most of the weight here is CO2 in the end. Okay? This is a way, if you have an organic material inside of your sample, like EVA polymer in a mortar, this is going to start to liberate CO2 around here. And this CO2 perhaps will react with portlandite that is nearby in the paste. And you're going to get carbonate. Okay? Things may happen. So we have to deal with that. So what we do in practical terms, say, okay, below 600 degrees centigrades, it's mostly water. And above that is mostly CO2. Of course, this 600 depends on your weight size, how big is your sample, on your machine geometry, and how is exactly what you are talking about in terms of carbonates. What kind of carbonates do you have? If it is carbonation from accelerated carbonation is one thing. If you have a natural limestone that is millions of years old is another thing. So you have to look carefully in each sample. And well, this coupled mass spectrometry is really handy. We can also put, instead of mass spectrometer, you can put FTIR to record. You don't see the chemical species, you see the molecules coming. But it's more or less the same. You can do more or less the same thing. Okay, I mentioned that it's difficult to compare a TG made from a Mettler Toledo TG with a result from Natch or with a result from, I don't know, TA. That's 3 big brands. Different geometry, different architecture, different sensitivity for different things. There's no one is better than other. There are different. We work here with, we have 2 machines from Natch. And it's difficult to compare. It's the same brand, but there's a different machine. The peaks are shifted. So you have to, if you are doing a research in one machine, you have to go to the end with that machine and with that procedure. Flow rate of pure gas is very important. Of course, depend on the size of the oven. Sometimes the oven is small, sometimes it's very big. So you have to be aware of that. Heating rate, this is your decision. Normally we use 10 degrees but it's per minute, but it's not, sometimes 20 is better. So amount of the sample, if you are testing a variable, keep the sample at the same size. You don't change 20, then 30 milligrams. It's going to mess up with the peaks. So you keep the sample about the same size. And you have to control particle size as well. And that's complicated because as the cement hydrates, it's harder to grind the particles. And it's difficult to control the particle size. So there's always little influence. You have to control, you do your best, and it's going to be okay. And the pretreatment, how do you dry it? It's a part of drying 100 degrees centigrade. You should never do that, because then there's no point. You can use another drying procedure if you're not looking for Ettringite. But you keep the same drying procedure all over the time. You can compare things, of course, unless you are looking for something very specific. So keep the standards, keep the machine, keep the preparation sample, control the particle size. Don't mess around with the size of the sample. These are good tips. That's it. Gypsum is really interesting because, you know, what you have here, this is the derivative. So below 100 degrees centigrade, it starts to lose water and one peak, and then this is two peaks overlapped. Because, you know, 140 degrees or something, 130, you start to lose, first you lose 1.5 molecules of water, then you lose the remaining half molecule of water. This is hemihydrate, and here goes to anhydrate. But the peaks overlap, and this is 20 degrees per minute. If you do another test, same machine, 5 degrees centigrade per minute, you can see, well, peaks goes down, because this is not a stable situation. You are hitting things all over the time. The faster you hit, the higher temperature the peak will be. So peak goes down, but you can almost see the two peaks. It's 5 degrees centigrade. Takes 4 times more to do this test than this test. But then you can do this. We have this here. We did a few times, because the way to do that is you put the gypsum inside of a sealed crucible. The vessel is sealed and have actually I think it's 30 micron hole on it. And net charge for each one, if I recall right, like 45, it's 10 euros for each one, okay? And you sometimes need quite a lot. So it's quite complicated, quite expensive machine. We try to, because a sealed cup is easy to do, the problem is the 50 micron hole. If the hole changes, it doesn't change. What happened here is you hit very fast, so water is going to be released from the gypsum, the hydrated water go to the atmosphere. Instead of going to the vent, you create a water vapor atmosphere. It's like a pressure pan. And this water vapor atmosphere, it moves the second peak a little bit far away, okay? So if you do that, you can clearly separate the amount of hemihydrate and anhydrate. This is very interesting to do, but if you try to do this in a cement, where it's really, really interesting, it's very difficult because the amount of gypsum you have in a cement is too low. So you don't get water enough to make this pressure. So you have perhaps work around, put another source of water that decomposed before. Because if you just leave the gypsum that is inside of the cement, you never got high pressure enough to postpone the second peak. But this can be used, and it's useful. But then you have to stop the test. For gypsum, there's no point to go above 300 degrees, unless if people are mixing limestone in gypsum, as they are doing nowadays in São Paulo. They take a bunch of gypsum from Pernambuco, and nearby São Paulo, they put some dolomite on it. And doesn't matter for the guy that is applying plastering in the surface, but it matters from research. So you have to be careful with gypsum nowadays. And what happened is here. So this is the weight loss. 5, in the end, this should be the same. The variability here is the experimental error you have. Because it's the same material, the weight loss, the total weight loss will be the same, but of course the steps will be visible. That's the point of it. But so you have the experimental error here. If you really have to go, now you have to do a lot of repetition. So this is the amount of gypsum you have, and this is the amount of hemihydrate in the system. So you can easily see the proportion if you do the right calculation. Here is the sample size. So 0.5 milligrams you are here, 3 milligrams you are here, 10 milligrams we are here. You see, things, they are starting to show up. So it's better to have a little bit larger sample. And we can go to 1,000 milligrams, but then it's, the peaks get wider and you lose sensitivity for peaks sometime. So depending what you want, you can play around with the sample. What is interesting is the weight loss starts about the same temperature, but ends in a very different temperature. There are a very simple reason for that. Heat has to diffuse from the oven to inside of the sample. The bigger is your sample, the longer time will take to the heat, to the temperature in the oven arrive inside in the sample. So and the oven is moving all the time, so your peak gets wider. That's the reason. And this is, well, we never do that. This is absolute change in temperature. It's about the same. Pretreatment, I think Karin already mentioned it. If you stop hydration using ethanol, you are going to have calcium carbonate. Because the ethanol will decompose, here. This is the ethanol decomposing, and then generates CO2 inside of the cement. And the CO2, in trying to find a way out of the system, will carbonate the calcium hydroxide that there is around. So instead of having Portlandite, you reduce Portlandite a bit and you increase carbonates. Okay? And that sort of thing happens if you have a lot of organics inside. Sample, I'm working with fiber cement that is reinforced with PVA fiber or PP fiber. And of course we have 70% of filler on it, but in the end we always have we have some carbonation. That is not really from the sample, is a result of this reaction inside of thermal balance. We have to live with that, at least we have to know. And here you should avoid ethanol. So remove with ether. Freeze drying, well, freeze drying is not a standard procedure. You can have different machines, different vacuums. It changes a lot and sometimes it doesn't work very well. So you can use freeze drying, but you lose information regarding CSH and ettringite. So it's a complete different peak. We use it a lot, freeze drying here. And then nowadays we are getting more beautiful peaks. Yeah. So we lost information on the time. And as Karin showed before, when you do freeze drying, this is XRD, and you see the baseline going up. This is ettringite. Ettringite disappears. And this is monocarboluminate, reaction between the limestone and the cement hydrates. So you lose it all. And of course, if you lose it here, you're going to lose it here. Well, oven drying, one day, 105 degrees centigrade. almost all your combined water with CSH, that is by far the most important hydrated phase in cement. Almost all is gone. It's really gone. So it doesn't matter if it is in the ASTM standard or lot of paper published with that. This is, if you want to measure things, you cannot destroy things before measuring it. And this is, the standards have been developed to control, to quality control in real building sites. They are not being designed to promote the advance of science. You can do science, good standards, doing good science, but the opposite, it doesn't work like that. So never do oven drying. And then if you have slag in oven drying, and you drive the powder long enough, you are going to oxidize all the sulfur inside, so you completely change your composition. It's okay to do oven dry if you are in the middle of nowhere and you want to check the water cement or check if there is something going on. But otherwise, forget about it. So you got carbonation, and then you have the total removal of the, almost all removal of the hydrated water. It's the integrate, if you integrate this, you are going to have the weight loss. So the area here is the water you lost from the total, what you are seeing. This is a derivative curve. So you integrate it, you got the mass change. So it's amazing. Well, freeze drying is also doing some loss. And if you try to recalculate this is CSH, probably is hydrated, produced by hydration only C3S or something. So it's pure CSH. And depending, you know the stoichiometry because you know the reaction, that's only calcium and silicate to react, and you put water, so you know things, it's not cement. This is what you lose 0.5 molecules of water just to doing freeze drying. And this is about CSH, it's like ettringite, it's very difficult to measure. Storage time, and we are talking here the amount of carbonates, 15 minutes in the air, and here is 2 hours in the air. So you ground, as Karin mentioned, you ground it, you put inside a container with, I don't know, something like very low relative humidity and something to suck out the CO2. You have to do that. Otherwise, it's going to carbonate. So that's very, very important. The difference is in Portlandite, in 15 minutes, there's some loss, but not so much. 14% of Portlandite. In then 2 hours, 11% of Portlandite. It's a huge change. Isopropanol, waiting time, same thing, and let's go to 16 hours. You see the carbonation peak increasing here. The carbonation peak increasing here. And Portlandite, you don't see much change, but you see carbonation changing, and you see here, the composition here, probably some ettringite carbonation. It carbonates very fast and lose a lot of water. So it's a huge influence. This is in the autosampler. That's just to leave. It's like 110 minutes or 120 minutes for each test, so it takes a while. So if you want to store, you ground and you store in a desiccation and you put in a vacuum and you leave 31 days, you think it's okay, but it isn't. Because your vacuum is not perfect. When you do high vacuum, you are going to destroy here. You see, you lose ettringite also. So I think the best thing is to do on spot. Recommendations, use the same device, heating rate. We use 10, you can use 20. Sample weight, 50 milligrams. I think it's good. depending on your thermal, your balance. If you really want to see an admixture on it, the organic decomposition of an admixture, you are going to need 1 gram. And we have a balance for that with 1 gram. You can see the grinding admixture that they put in the cement to ease the ground, to reduce the energy. You can see it inside. Gas flow, particle size, pretreatment. Storage time you have to reduce. Now, same day, stop hydration with isopropanol, ethanol, fast drying to remove organics sometimes, organics that use here. That's like here, Karin recommended 15 minutes, 40 degrees to get rid of the isopropanol and the ether. No freeze drying, no drying, if ethering is present, and it's always present. And there's a book chapter on it. TGA is good for many things, but like XRD, I think worse than XRD. These are TGAs, DTGs, from pure phases that are present on cement. What we see is like that, but these are the result of the sum of these different curves. So what you measure at every moment is the composition of different things, a combination of things. And well, it's CSH, ettringite is here, gypsum, this is calcite, this is pure portlandite, and so on. Here you have brucite, calcium hydroxide, and this is magnesium carbonate, and this is calcite. Most of the fillers that people are putting in cement nowadays are, well, have magnesium, some of them dolomitic. So this peak is going to be close to calcite here. It's even more complicated. This is the result of carbonation. You have calcite, but you also have vaterite and aragonite. Accelerated carbonation gives quite a lot of vaterite and aragonite. It's not water soluble as many people think, but are different. There are different volumes. And in the end, they influence in your spectrum, because these two, they decompose at a lower temperature than calcite. Calcite starts above 600, but this one, they can be as low as 400, depending on your machine. And they also have allotropic transformation here. That is exothermal. You can see in DSC, very, very easy. So when you have accelerated carbonation, you don't apply the 600 degrees rule. You have to look carefully what you are going to do. This is CSH. The composition of CSH is from wollastonite. That is a mineral that is calcium silicate oxide. And then you hydrate, you get CSH, things like that. And another CSH. So depending what the composition of CSH, you are going to have different peaks. And if there is really, from cement, you always got some portlandite. But this is CSH. And you see, most of the water is released here, but the derivative here is never zero. It's never zero. It's always losing something. It's always losing zero, or zero is here. It's never zero. Meaning CSH is going to lose water up to 700 degrees centigrade. Not much, but a little bit. Ettringite is in thaumasite. Ettringite is more common. In here, it's a really sharp peak. Most of the water is gone. And then you have some more water, 250 in this machine. And this is normally close to 100 degrees or a little bit above 100 degrees, depending on the size. So this sharp peak is ettringite, and the wider peak is CSH and other things. Monocarbonate, monosulfate, stratingite. This is a mixture. You see here different, you can more or less cut between it. But actually the peaks are like that. You see the reactions in each step, but this same reaction occurs in the three phases. So you will never know from which one what is going to be decomposed at given temperature, because they are same variety and same things, and they are intermixed. So these are the derivatives of everything you saw so far. So weight loss is the integration of all these curves, considering the mass presence of each one that we don't know clearly. We can do thermodynamic simulation to have more or less, I guess, how much we have from each one, but it's different scenario. And then you got magnesium. We always got magnesium. In Brazil, we have more magnesium than everybody else's, but we have up to 6.5% of magnesium oxide in the clinker. Yeah, in the cement. But it's going to be more or less in the clinker. And then, but it's the maximum in the standard. And most of Europe is, I think, is 5. Yeah, in some places 4.5. So these are important as well. I think this is more important because what really you can measure from TG that is isolated more or less is the portlandite decomposition. And this can help you to track hydration. You can track pozzolanic reaction very easily because it's going to consume portlandite. You can also have a good glance on carbonation. Okay, so this is very good. And this is what it looks like. This is, you can think hydrated lime, PA. And these are the peaks. In this case, it's 450. It's a small sample. If you go to a 1 gram, it's going to be 550 because it's a bigger sample. So you have mass here, mass after the peak, then you can calculate it. Okay, it's just stoichiometric estimation. You can see how much is it. But if you are, have a mixture, a cement, so you have CSH losing water all the way to, let's say, 600, 700 degrees. On the top of that, you have portlandite decomposition within this range. Okay? The problem is Natch equipment have a software to do the analysis. And the default approach is stepwise, which means the onset of the peak is here, so this is 0, the end is here, and then I just measure this difference. This is what the machine does to you by default, most of the machines. If you are using a pure portlandite, it's okay. But if you are using cement, it's not okay. Because you have, here, you see, it was losing weight before and keep losing weight after. So this difference is a result of this plus this. There are 2 peaks overlapping. So this, in this calculation, you got 29%. And the other in the software, other option in the software is like that. And they do here, but they take this difference here on the beginning of the peak, on the onset of the peak. Okay? What people from NanoSem find out that you do this and this, but instead of measuring the difference here in this point, on the onset of the peak, you measure in the middle of the peak, in the center of the peak. The value is a little bit lower, so it's like 23 grams of portlandite, and here it gives you 29 grams of Portlandite. The problem is you have to do this by hand because the machine does like that. Okay? It's written in the book. There is, I think, 5 pages on that in the book. It's very good. We did have some results that was very difficult to explain. And then after we read the chapter in the book, we corrected the results and everything became so simple. So it was a problem on the methodology. And then this is what they are showing, 2 cements. Supposed to have an animation here, but it's gone. So it's tangential is the method they recommend, 18.7. Stepwise, that is the default, 23. That is too much, 23. Karin already mentioned it. What the TGA does, 100% is clinker plus water. If you are following hydration, you take samples for, let's say, 1 day, the amount of water is 1. 7 days is higher, 28 days is even higher. So your amount of clinker or binder is about the same. So you have to correct to use the same basis. If you want to compare things, your 100% has to be the same all over your system. And this is, Marialba fight with us for 25 years on that. You have to do this on dry basis, yeah, non-volatile basis, and this is what you have to do it, actually. So you do the correction, and they suggest a correction using the 600 degrees. But if you are looking for carbonation, you have to do your reference temperature after the decomposition of calcium carbonate in 1000. Then depending, but you have to use the same temperature all over the time. So your weight loss is not going to be a percentage of the initial mass, but speaking is going to be the percentage of the final mass, the non-volatile weight, or the 600 degrees weight. And that makes things okay. This 600 is only good if there is no carbonation going on. If there is carbonation going on, use 1000, 1050 centigrades, something like that. So this is experimental results. If you do percentage of the wet, and if you do percentage of the dry. It's a huge difference. And here is completely wrong because your reference is changing all the time. It cannot be. It has to be the same. Blast furnace slag. Again, this is a mass spectrometry. So you are heating your cement. This is the weight loss, gravimetric. And at 650, the weight starts to go up again. And why? You see, sulfur oxide is coming out, and it releases, and it's going to increase the weight. So you should know that, and you have to. Oh, so you see here, sulfur is going to consume it here, and it's going to combine, and then the weight goes up. So what you have to do is, this is in nitrogen, then you put in oxygen, it even goes much higher. Yeah? But theoretically, there is no oxygen because you are feeding nitrogen to the oven. This is in theory. You always have some contamination, you always have some oxygen from the beginning, and there's oxygen everywhere in all the sample. So it's always have oxygen. So if you feed oxygen, it's even worse. You do in nitrogen. If you do vacuum before, it's better. Not all machines allow to do vacuum before, but it can be done. And there are different ways to control, and you can increase the amount of nitrogen if you want. Changes a little bit. You have to calibrate the entire machine again because it influences in the weight, because you have a drag of the nitrogen moving inside the machine. So it's complicated, and you But if you know what's going on, so you know you can compensate for that. This is for the ones that use fly ash. And fly ash has, especially in Brazil, quite a lot of carbon on it. And the carbon, well, in nitrogen is not going to react if there is no oxygen. And it's graphite, it's not volatile carbon. It's not like a plastic that has volatile things that is going to decompose at low temperature. This is a carbon that came out from an oven. So it's a high temperature, should be stable if you have no oxygen inside. If you put oxygen, you burn the carbon and then you generate CO2 and you generate energy inside the machine. Machine corrects itself, but it's a completely different system. You can do, and sometimes you can do just with oxygen to know how much organic matter you have inside of the system. It's very easy. So you have these oxidation reactions inside of the TG. And this is a DSC, or here is DTA, but it could be a DSC. You are heating blast furnace slag, so that's almost no weight loss, because blast furnace slag, it's probably granulated blast furnace slag, so it's glassy blast furnace slag. But in order to granulate, they take the slag, it's a liquid, 1500 degrees centigrades, and they put in the water. So in the surface, you always got some hydration because it has been cooled down using water. So you're probably losing 1.5% of hydration by hydration. Yeah. But at the same time, you see here there's a peak. There's not much weight loss, but this is the peak, is endothermal peak. It's a devitrification. What is going to happen here is very simple. The glassy part is going to crystalline, to becoming crystalline phases around 800 degrees centigrades. If you know that, you can calibrate that. It's possible to measure by Ritual, whatever, how much glass you have in the slag. You can, in a TG, know how much slag you have, how much slag, glassy slag you have. Because what really matters is the amount of glassy slag. But the crystalline slag is not going to react. It's like a basalt. It's mervinite, a kermanite, millilite, things like that. So it's very handy. So if you are going to go to do TG, to phase identification, you have to be aware that we don't see phases in TG. You see mass change due to heating. Or you see heat flow associated to temperature changes. You know, it can be anything. It's like XRD, you know. In order to interpret an XRD, you have to know the chemical species present on it. So chemical analysis, XRD. If you combine XRD with TG, you can take quite a lot of data. Many people just take the peak positions or decide, okay, hydration ends at 550 because it's written on Taylor's book. It's written in Taylor's book. But it's for his own TG probably, depending on the TG you are using. So you have to know what you are doing and you have to understand what are the reactions. You have to do carefully. You can quantify calcium or Portlandite. I think it's easy if you do properly, if you don't carbonate, if you do the proper interpretation, it's okay. You can quantify more or less the carbonated phases because CO2 peaks are above 600 typically. So you can see. You can see there is magnesium carbonate inside or not, just for looking into the peak. You can identify organic admixtures because they are going to lose some weight at some temperature, like 300, 400. There's a peak over there. So you can see a lot in a TG. But quantitatively, you can do that. I think there are two good information. Amount of Portlandite, three informations. Amount of calcium carbonate, amount of CO2 is quite precise. There is some overlap, but it's very good. And you can know the amount of combined water. So if you want to track your reaction, the combined water is really, really good. If you are investigating a new supplementary cementitious material, and doesn't matter if the Brazilian standard allow you to test a pozzolanic material by compressive strength, yeah, because dry mud do have compressive strength, right? So it doesn't make any sense. You mix, you let hydrate, you run a TG, you know the combined water. You have your clinker as a reference, you know the combined water of your clinker. You compare the two, and you know what is the contribution of your supplementary cementitious material to the chemical reaction of hydration. It's a primary information. I see a lot of paper based on the Brazilian standard that I hope the Portland Cement Association support our claim to withdraw this standard because it's really a problem. And it's no chemical reaction possible. So TG allows you to see, is that material reacting or is just diluting the cement? It's fine. We deal in the lab a lot of fillers. We like diluted cement. It's very cheap. It's very effective. But you cannot claim a chemical reaction or call the pozzolan just because it gave some strength in a standard test. So this is, I think, it's a very used equipment. Well, the book chapter is very good. It's really, really good. And I think all of us, we have to improve sample preparation. We have a problem. If you don't have in your lab the TG, so time is a problem. So we have to plan for that. And this requires, a different approach. And there's a lot of paper here. And Marialba has some notes that she can hand over to everyone, I think, that she used to teach. So that's, I think it's a good method.